All right, welcome to the last session 5 for Advanced Track, the last workshop. And today we're going to be talking about max flow. Once again, we have the slides linked, so if you want to follow along. And yeah, let's just get started. So what is max flow and what is the problem that we're trying to solve today? So the big idea is that we want to find the maximal flow in a flow network. So what does that mean? So a flow network is a network. A flow network is a special type of network, and a network is a directed graph with weighted edges. I assume you guys know a little bit of graph theory, so I'm not going to go into it. But instead of the weights representing distance or cost, such as like in a map where you're trying to like find the shortest distance using Dijkstra's, the weight represents the capacity. And that capacity is going to represent some level of flow. So the network is a flow network if we have one node assigned to be a source and then one to be assigned to a sink. So below you can see there's different weights. So the source is on the left here, and let me make this laser pointer. All right. So this one is the source here, and then the sink is on the right here. And you can see these are directed edges, and the capacities are 7, 5, 3, and the zeros there we'll get to later. So you can see the direction matters for this. And what is a maximum flow? So first we need to define what a flow is. So a flow assigns each edge in a flow network a non-negative value such that the following constraints are satisfied. So the flow of each edge does not exceed its capacity. Its capacity, as I said before, was the weight on the edge. The incoming flow for a node equals the outgoing flow for non-source and non-sink nodes. And then there's a special case for source nodes where there's only outgoing flow and there's only incoming flow to the sink. And the maximum flow is a flow with a maximal possible value, where the level of the flow is basically how much flow is leaving the source, or equivalently how much is entering the sink. So let's give an example. So we can kind of think about this as a collection of pipes and water flowing through those pipes. So each edge is like a pipe with specific diameter. If the diameter is larger, then the capacity is larger, more water can flow through them. And then the nodes are like junctions. So since a junction has like 0 size, it can't collect and it can't accumulate water there. So the amount that enters at the junction has to be the same amount that leaves it, except for obviously the source and the sink. So by using this analogy, we can kind of see how the constraints 1 and 2 are created. So yeah, does anyone have any questions so far? Good. Does that make sense? All right, so how do we find this maximum flow? So we're going to follow this method called the Ford-Fulkerson method. Note that this isn't an algorithm. This is just a general idea on how we can reach this maximum flow. So we need to find one more thing, the residual capacity. And the general intuition is that it's just the leftover like available space that you can push flow through. So if you have a pipe that's operating at half capacity, then the residual capacity is just the other half. Or if it's 2/3 full, then it's just 1/3 of the capacity is left. And we just keep track of how much available how much available water we can push through. What's special about the residual network is that it's also pointing in the other direction. So in the same example, if we have a pipe that's half full with flow, then there's going to be an edge that's going in the direction of the pipe that's like 1/2. And then there's going to be another edge that's going backwards. It's also 1/2. And there's a reason why we keep track of that. So from this, right, with this residual capacity, we just create a network out of these capacities, just like how we did that for the original flow network. Don't worry, we'll show an example. But first I want to just like kind of get through it and then you can kind of see. So the Ford-Fulkerson method will use all these definitions we talked about. So it'll set the flow of each edge initially to 0. So it's just going to be no water is going to the network. And then it's going to look for an augmenting path from the source of the sink in the residual network. So an augmenting path is a simple path from the source to the sink where every edge is positive. So in this case, basically, if you can push water through a path that's available in the residual network, and just push it through. And we increase the flow along that path, and then we repeat. And repeat until there's no more paths left, and we can't increase the amount of flow going through the network. It's kind of like a greedy type solution, and we can actually, and this is surprisingly works for all cases. And what I mean by increasing the flow is that you increase it to the minimum residual capacity along the path. So let's do an example. So this is the original graph from before. So you can see the residual graph is basically the exact same as the original flow network graph. So we're gonna have 7, 5, and whatnot. So this right here is a augmenting path, and it's gonna have you can only push 5 flow through this because it's limited by this pipe. If you push any more, it can't go through that middle pipe, even though we can pass 7 and we can pass 8 flow through the other 2 edges. So we're gonna apply it. Then you can kind of see this edge is filled up, and then the other 2 are not. So we can pass more flow through them through a different path, maybe. And we can identify another path. This is another augmenting path. And we have this being limited by this 3 here, this and this 3 here. So we add that again. And then what's interesting is that we actually, if we just look at these edges that are pointed as they are, there's actually there's no way to increase to find an augmenting path. But actually the flow can be 1 larger than this. And that's if you take, oh wait, sorry. Nah, I got ahead of myself. You can have 1 more, and you can, there's this one that's 4 long. Okay, there you go. And now there's no more, wait, because there's a 4 here, right? And then there's a 5 here, and this is maxed out as well. So, but we can actually find 1 more. And what's interesting is this red edge here. This is going opposite in the direction. So how can we do this? And it's because right now we're just looking at the original flow network, and we're not looking at the residual graph. And what's happening in the residual graph is that there's an edge that's being pointed opposite in the direction that has a weight of 3. So there's no edge pointing this way, but there's an edge pointing this way, it's 3. And the idea is that you're correcting a mistake you made earlier, where you can, instead of using this flow from here, right, you're going from S to D, then to A. You go from S to A, you send something along S to A, and you send it directly. Yeah, you send it directly from S to A instead of going from S to D to A. Then the flow that's going from S to D can go to C. So it's like you're creating this path and then this path. You're doing 2 paths at once. And yeah, so then we subtract it from this, so we get 2 here. And also another way to see how this is fine is if we think about the constraints we talked about earlier. We have to have the amount that's going in equal to the amount going out. So before, right, these other increases, they would just increase the amount going in and increase the amount going out. But for this case, what we're doing is for A, we're going to increase the amount going in, but then decrease the amount going in. So it's actually going to even out. If you think about it in terms of this red edge being decreasing the flow entering A. So these are all equivalent. Does this make sense, this process? Cool. All right, great. And now there's no more augmenting paths, so we're done. So our max flow is going to be the maximum amount that's going in here. So it's 6 plus 4 is going to be 10. You also look at this one, 6 plus 4 is 10. So the amount leaving is equal to the amount entering, which should be fairly clear. So now that we have this method, well, how can we implement this into an algorithm, right? So the big idea is how can we find these augmenting paths, right? We know that if we just keep finding them, we'll eventually reach the final solution, but how can we find these augmenting paths? Does anyone have any ideas? The 2 people here.
Sorry, can you repeat what an augmenting path is?
Yeah, so an augmenting path is a path in the residual network where every edge is positive. So basically, if you have a path from S to T, from the source to the sink, that has like room spare in all of the pipes that you picked in that path, you can push some flow through that.
Okay.
So,
What's the residual network?
So the residual network is kind of like the leftover. Where is it? Here. So you can kind of see a better. We'll see a better picture of it later, but the idea is that it represents like how much flow can, how much more flow can go through an edge. So instead of having the flow currently through the edge and then its maximum capacity, we just subtract the two, and then we get like the leftover like potential that we have. We can push more flow through there. Yeah, we'll have a better photo coming up. Now. Yeah. So any suggestions on how to find this path? How do we look for paths in graphs?
Keep track of for each edge how much flow you're pushing through each edge.
Yeah. So Tommy made a good suggestion. So we have DFS, right? So we want to see if it's possible to basically reach it by just keeping track of, is the edge positive, and we just keep going and see if we can reach it, because the DFS will search all paths. But Ryan also gave a good suggestion, BFS, and that's going to be what we're working with. And yet the problem with DFS is that we won't find the shortest path, because DFS just looks for any path and it just traverses down the tree. And notably, we don't need to use Dijkstra or anything, because all the edges are like basic unit length. We don't really care. They don't have a particular length. Once again, the weight corresponds to the capacity, not the distance. So BFS. So what we can do is we can just, so the pseudocode for this algorithm is just as follows. We have some max flow that we're trying to find, and then we just look for BFS, and this is, or look for an augmenting path. And this is when we call BFS. And when we look for that, we go through the edge and we increment and decrement. This is updating the residual graph and then adding this new flow to the next flow. And it's pretty straightforward. And all we need to do is kind of just implement BFS as we know and love. Yeah. And the complexity for this algorithm is actually VE squared. And this is pretty hard. It took me a while to get this as well. So how can we figure out the complexity? So basically what the complexity of one iteration to this loop is just a BFS function, because adding this max flow, a simple path has a maximum length of V, because there are no loops or anything. So this is going to be O of V and then plus O of E, because the BFS takes O of E time, where E is the number of edges. And then we claim that the number of phases, so the number of loops that we're going to have, is VE. And this is a really weird concept. How can we get like O of V? Why can't we just keep running this over and over again and keep fixing and slowly getting our max flow closer and closer? And that's because, so the general intuition is that each augmenting path saturates an edge, and that means it fully fills up an edge, so no more flow can pass through it. So it's like maxing out a pipe and no more water can go through. And if we need to use that edge again, then the distance from it to the source will increase. And since it keeps increasing, each edge can only be used up to V times, actually V over 2. And I'll show later why. And so eventually we won't be able to reach any edge, basically, won't be able to use it, and there will be no more paths left. And I can actually give a good example. This camera is not working, so let's think about how I can do this. Yeah, okay. Here, let me see what I can do. So this is our graph here. And this is actually going to be our residual graph in the beginning. And what we can do is we can think about how this idea of saturating and like this distance is increasing, how that works. So first of all, we want to see what are all the possible augmenting paths that we can pick. And I claim that the set of like augmenting paths that we can pick is like this thing called, I'm going to call it a BFS tree. So if we go outwards, so I'm going to maybe draw this one more time. If we go outwards, all of the paths will basically be a bunch of like levels. So this is like level 1, and that's because it only takes one edge. At minimum, it'll take one edge to reach that. And we won't include this edge because we can already reach A with only one edge. And then we can continue. So B is at a level of 2, and C is also at a level of 2. And actually, we can include both of these edges because it goes from 1 to 2. And then we can include this edge here, and there's a distance of 3 to T. So this I'm going to call either like a BFS tree. It's not even a tree, it's like a BFS graph, really. Or, which we'll talk about later, it's like a level network. And you can see there's like different sets here, right, of equal distance. And the set of all graphs, like we can have this path, we can take this path or this path. So there are 3 choices, and these are all equally valid using Edmonds-Karp's, right? So let's say we pick one, right? We pick one of these edges. It's guaranteed to saturate one of the edges. So take, for instance, this edge. So if this edge is saturated, in the residual graph, this is going to get reversed. It's going to go this way. And since the shortest possible way to reach A and B is already in this BFS graph, and since all we're doing is reversing an edge, there's no way we can create a shortcut to reach A, right? So if for some reason we have a path that includes this, it's going to have to go through B and then go to A, which means the distance is going to increase to at least 3. And we're going to have to reshuffle this around like for future iterations. Does this kind of make sense? So the distance, this distance is going to increase because by adding an augmenting path, we're not going to create a shortcut to be able to reach B any faster. If we can reach B in a distance of 1, we would have already done so. Does that sort of make sense? Because all we're doing is adding kind of like backwards edges as we add the residual graph. And one of these is actually going to get deleted entirely. Maybe this one, maybe this one, maybe this one. And this happens for every augmenting path that we pick. So if I actually run this.
Wait, Robert.
Yeah.
Sorry, could you go over this argument again? Like in particular, like why couldn't we have a, like let's say we saturate an edge so that that edge disappears and there's only a back edge in its place. But then let's say maybe we decide on a future step to saturate the back edge and then that edge comes back. Like, why doesn't that happen?
Yeah, so it's not like these are flipping positions, like B is going to become a distance of 1 and A is going to become a distance of 2. It's that B, this node here, B will never ever, no matter how many augmenting paths we apply, the distance of B will always remain at 2 or increase. And the reason why that is because all the edges that we're introducing are going backwards. So in this like DFS tree, in this BFS tree or this level network. And that's because we've already reached A, we've already reached a level. Going backwards won't create a shortcut. Does that kind of make sense? That we can't like get somewhere faster by adding reverse edges, like back edges. And since it can't decrease, right? B can't decrease. The only thing that could happen is A increases. Either A remains as 1. Maybe there's another, I don't know. Let's say there's another edge here. It can't be a source, but pretend A wasn't level 1, but like level 2, and there's another edge here. Maybe A remains at level 1, but eventually all of its edges will get reversed, right? And then A might become a node in level 3. And it's actually guaranteed this, if this blue edge is the only edge that connects to A, it's guaranteed that A will be either level 3 or greater, or distance 3 from the source or greater. if we use that specific edge again. Maybe we can use different edges, but it's just that one specific edge is further away.
Okay, wait, so you're saying start from the original residual,
Yeah.
like starting from the original residual graph, we're going to construct some like monovariant function of the residual, like of the current residual graph, which is like,
this is,
turn it
these are
into-
all the edges that could show up in like a BFS traversal.
turn it into a BFS tree, and then like, or do BFS and then add up all the distances of all the vertices. And you're saying,
Or well,
each,
I'm saying like every path in this graph, in this new graph that goes from S to T, by applying an augmenting path, it will only add back edges, and adding back edges won't decrease the distance to from the source to each node. This is like really specialized. Yeah.
But so why might not all of the distances stay the same, and then you just keep iterating forever?
So some of the distances can stay the same, but it's specifically this edge. So if a future path uses this edge specifically, this back edge that came from the saturated edge in the augmenting path we picked, right? If it uses this one, this has to be like flipped around. If in the eventual in the new residual graph, it'll be a forward edge, and it's locked at this B here, and which means it'll have to be the length will have to be greater. The path length will have to be greater.
The path length to B?
To this edge, to this back edge.
Ah.
Because this back edge will eventually, this isn't actually here, but it'll eventually be here. And it'll be pointing forward. And it's like this, it's like we're taking this saturated edge and we're kind of just moving it to the next level. So instead of going from 1 to 2, it'll eventually be 2 to 3 or later. It'll be 2 to 3, 3 to 4, or any of them. And each time it's strictly going to increase if it's used again. And this process eventually terminates because there's only so many edges it can, or there's only so many levels in this level network or this BFS graph, because paths can only be so long. There's only so many vertices.
Just to check, the final point complexity is VE squared.
Yeah, VE squared. So BFS takes E time, and then this process by augmenting the graph results in no more augmenting paths exist after VE phases. And that's because each edge, right, can be moved up V times, actually V over 2 times. And there are E edges. So the number of augmenting paths we can apply is capped at VE, because the paths will keep, the path that includes each saturated edge will only show up V times, and that's for each E, for each edge. Yeah.
Yeah, what do you mean by a back edge? I thought a back edge was an edge in the residual graph, which is like a hypothetical.
It's in this new graph. It's in this. Well, sorry, yeah. It's also in the residual graph. Yeah, it'll be an edge that's going backwards. And this back, when I say back, it's like relative to this new graph that I created, where it keeps track of the shortest distances to each of the.
But what does it mean when you use BFS and generate a path that takes a back edge?
It takes it back. So yeah, so in the future, right? Maybe the only way to reach A, maybe the shortest path to reach A no longer uses this edge. Maybe it does something weird, like it goes like this, right? Or maybe it like, I'm running out of colors and it's getting really messy. Here, wait, actually, let me do this. So maybe it takes something like this and it goes backwards like that. It doesn't show up too well.
Like suppose that there are edges, directed edges in that direction.
Yeah, something happens. This edge shows up, right? And yeah, this edge shows up. Maybe we use it, or maybe these edges disappear, right? Then like this is the only way to use this to reach A.
Okay.
Obviously, this isn't going to be that useful because A wouldn't have any way of connecting to the source or to the sink.
Yeah.
But this is what I mean by reuse, like using the backend. So it shows up again in this BFS graph. So it shows up as a potential augmenting path.
Okay.
Oh,
I don't
okay.
fully understand it though, because there's no edge in the original graph from B to A.
Yeah.
So like, what do you mean take a back edge? Like, there's no back edge from B to A.
So when we update the residual graph with an augmenting path, we kind of revert, we have that like backwards edge. Let me see. So do you have the slides? I could just show you on the screen. So when we do this red edge,
Yeah.
in the augmenting path or in the augmenting graph, I'm sorry, this doesn't show up for Zoom people because I don't want to switch my screen share, but the edge actually goes like this. It goes downwards and has a weight of 3. And there's no edge that actually goes upwards because this is saturated. So instead of having an edge that goes from D to A, it'll go from A to D.
Okay.
And it'll have a weight of 3. And it'll show up in the residual graph. Yeah. And don't worry if the level network, the BFS graph thing doesn't make too much sense. We'll come back to it again when we talk about one more algorithm. That's general idea. Yeah, this is really complicated. So don't worry if you don't get on the first try because it took me a little while to wrap my head around it. It's kind of a little tricky to explain. But yeah.
So I think something that I think I understand what you're saying now, and when you use that, let's say at a later point you're using that highlighted light blue path, then the BFS graph will look different, and you always only use edges that go from left to right in the BFS graph, and so the BFS graph will look different, and in that different BFS graph, again the distance to the edge from A to B will increase because we're swapping it from going left to right to left.
Mm-hmm. Yeah.
Okay.
And I think another point of intuition is that the distance, every time you add an augmenting path, the distance from the source to any node is either going to stay the same or is going to increase. And one of the edges is guaranteed to increase. One of the nodes, or one of the edges to one of the nodes is guaranteed to increase. And that eventually terminates.
It seems tricky to think about, or if you just look at nodes, then it's possible that an augmenting path does not increase the distance to any node, right?
Yeah, it doesn't. Yeah, not necessarily. It's like one of the edges to one of the nodes, which is harder to see. But yeah.
Okay.
Yeah.
Cool.
So we want to look at it edge-wise. In the future, and in the next algorithm, we'll look at it node-wise. But in this one, we have to look at the edges. Okay. Cool. I hope that makes sense. And we're going to do an example problem. So I'll give you guys, let me share a screen again. Give you guys a little bit of time to read the problem and think about how you would solve it. Okay. Hello. I hope you guys can hear me. We're back. I hope everyone is able to read it. So how do we do this? We just implement it. So the problem is pretty straightforward. It doesn't really give nice bounds or anything that tell us that this is going to work, but you just kind of hope. A lot of these Maxwell problems are you can't really do when you do the calculations for the time complexity, it's very much an upper bound, the OVE squared. It actually runs a lot faster than that, depending on the graph. There's only a few edge cases where it's it'll take actually that long. So yeah, so what we can do is we just construct the graph by only adding edges with UCD greater than 1. And yeah, and actually I'm going to implement it with you guys so that you guys can see how to do it. But normally when you're doing Maxwell problems, you don't really implement the algorithm. You just kind of find a good template and you can just construct the graph. And that's generally the more interesting part of Maxwell problems, is actually noticing that it's a Maxwell problem and how to adjust the problem setup so that it is Maxwell. Okay, so I'm going to do it. So this is our Maxwell algorithm. This is Edmund Ford, Edmund-Karp and this will be a BFS. So we can do our BFS first. So we need to initialize the parents. So right now we want to keep track of the path by doing like a BFS. So we want to keep track of parents of all the nodes. Let me do this. Okay. So we want to set this all node 1. The parent source node 2. And we need to open the queue. Keep track of the node that we're looking at and the flow that we can currently push through it. Push the source, and then since the source, any amount of flow can push through it, we just put infinity or use int max. Now we create the BFS loop. So while BFS is not empty, we're going to pull out, not BFS, while the queue is not empty, we're going to pull out the node, so the current node, and that's going to be this one. The current flow that's pushing in. We're going to try all of the edges. So adjacency. And we want to search all neighbors. So if it's already been visited, then we don't need to do this. So it has to be not visited, and the flow needs to be positive. So the capacity from the current one to the next one has to be greater than 1. It just has to be, yeah. And then what we do is we just push the flow through. So our new flow is the minimum of how much we can push through and our current flow. And then we push it through. So we just add this. And we can also set the current. Okay. And if we reach, and then one more thing, if actually you can do this. If the next one is equal to the source, or to the sink, right? We've reached the sink and we can push something through, then we return. It is guaranteed to be not greater than 1. Guaranteed to be positive, so we found an augmented path. Okay, and then if it's not found, if we tried everything and we can't reach this sink, then we just return to that. So that's our parent of T. Yes, we want to do that. So we'll do this before. Good catch. All right. So then this part. So we just create the array. And we want want to keep track of the max flow. And we want to for a while. While full flow, we set this to the amount of flow you can have. So if this is 0, right, there's this, it'll break out of this loop. If not, is this big enough? You guys see that? Okay. While there is still space, right, then we push it through. So start at the sink while and then we update the flow. So capacity and minus equals flow, and we flip the reverse. And then we add the flow that we found to that flow. That's done. We'll just return it to display. Hopefully this works. Any mistakes? But yeah. So now we need to construct a graph. So let's look at the problem statement and figure out how the input is given. So okay, so it gives n, and then it gives all the values. Yeah. Okay, so actually just import n, read in everything. So we'll just read it in. Well, we'll just ignore it. It's fine. It's probably fine. We can do it this way as well. You guys have the problem? What's the maximum number of values right now? Okay, and then we need to construct the graph. So what we do is we're going to initialize capacity. Yeah. Capacity. Size the adjacency list. We're going to be keeping track of all of the pairs that way. Oops. And then we're just going to add all of the so the capacity, if I is not equal to j, and the GCD is not equal to 1. So we can use the pre-built GCD in C++, while if j is not equal to 1, we're not in. So we do a capacity and is equal to GCD. is it going right? Undefined. That should be right. Is it 1 underscore?
It might just not being picked up by the syntax highlighting.
No, probably not. And then we add the address to this. So y. And since we do this in both directions, we don't need to worry about doing it in both directions here, because it'll be in the for loop. Finally, we need to find the source and the sink, which is a little annoying. So we need to keep track of the minimum and the maximum. So we'll just do it like this. Min. And this should hopefully work. So we just see out max flow source to sink. And ideally we should work. Okay, that's not working. What we're gonna do is we're just gonna look at let's do it. Oh, did I not pop? I didn't pop. Possible? No. Okay, well. Debugging on the fly is terrible. Huh? Diff it? Do I have diff? This is Windows. There's no diff in Windows. Oh my god. Oh, do I not update this? I also don't update this. While I didn't do this. Why you never implement algorithms. Yeah, you just use your implementation. Oh, I did this differently. You know what? This is okay. Okay, maybe this will work now. All right. Oh, wow. Amazing. Very good. Very good job. So that's good. All right. So that's how you implement Edmonds-Karp totally legitly. Now let's move on to Edmonds-Karp. All right. So now that we did Edmonds-Karp, I want to talk about another special case of max flows. So one thing about max flows is that you can be applied to this thing called min cut. So what is min cut? That's a lot of words. So the basic gist of it is that you have a graph and it's a weighted graph. And what you want to do is you want to split it into two groups where these two groups, you sever all the edges that are connected in between the two groups. So all the edges can only connect to the edges in within the groups that you decided. And your cost is going to be how much the cost of all the weight, the sum of all the weights of all the edges that you had to delete. And this is just a picture. Oh my God. This is just a picture of it. So you kind of split it into two groups, right? And these are just edges. They don't actually have to be directed. They're generally just like undirected. You cut them. And we can think about this as a max flow problem. Also, one constraint is that one node has to be in one of the sets, and then one node has to be in the other set. And those are going to be our source and our sink. So we can think about this as a max flow problem. And in a general sense, if we have a maximum flow in this graph from the one special node to the other special node, then if we remove all the edges at full capacity, we have a guarantee that there's no augmenting paths, which means that it's fully separated. So our answer is at least bounded above by this maximum flow, but the theorem says that it's actually equal to it, and there's no other way to do it cheaper. This is useful for questions that are asking you to like separate stuff or find some minimum of some quantity. You can sometimes convert it into a min cut type question. Yeah. That's basically all I have to say about that. So now on to Dinic's algorithm. So this is another algorithm for solving max flow, and this does it a little bit faster. And this is why you should always use Dinic's and not Edmonds-Karp. So this is an improvement. So it goes from VE squared to O of V squared E. And it's a really interesting change, right? How could you go from the edges? Normally when you do this type of change, it maybe goes from like n squared to n log n. But this is like kind of jumping the entire thing where it goes from edges to vertices. We're changing an E to a V. It's pretty cool. So we have to define more stuff for this algorithm. So let's get into it. So a blocking flow is a flow. So a flow is not just one path, right? We talked about it before. There's like a flow and there's a path. A flow can be a single path that's like saturated or has one edge that's saturated, but it can also be a collection of paths. So a blocking flow is a flow over a whole network, right? Where every path from the source to the sink contains at least one saturated edge. So in other words, you can kind of think of intuitively as like there's no more augmenting paths, but this is only true for acyclic graphs because there's some special case where you can go backwards or something, and you can find an augmenting path. So this is a max flow for acyclic graphs. I won't really go into it, but this special property of blocking flows is really useful. And then also we're going to define a layered network, which I talked about before, and we're going to define it as based off of a network as only the positive edges from the shortest path to the source node. This is what I was talking about before with the BFS tree. It's like you have columns of nodes that are like increasing distance apart, and we only keep the edges that are a part of that. So it's coming back. Okay, so let's give an example. So this on the left is the original flow. In the middle is the residual graph. And the one on the end in red, this is the layers. So the source is going to be a distance 0 away from the source. Then these two nodes, you can reach them in one edge. These two, you can reach in 2 edges. And the source is 3 edges away. And we only include the edges that go from one layer to the next. It only increases in the layer number. So that's why it's called the layered network. So we deleted this one and this one because these don't connect. These connect from 1 to 1 or 2 to 2, not from 2 to 3. Okay. So with this defined, we can explain the algorithm. So for each phase, so we're just going to repeat this process. We're going to construct the layered network of the residual network. So this is the second graph here. And we're going to find the blocking flow, any blocking flow of the layered network, and then add that flow to the original network. And we're going to keep repeating this, and we're going to basically add up all the flows, get a superposition. That's going to be our answer. Once there is no more, once there's no possible path from the source to the sink. So the blocking flow is like nothing, right? And the claim that we have for this algorithm is that the number of phases is less than V. I'm not really going to go into this because it's a little complicated, but the intuition that you can have, is that the distance from the sink from the source strictly increases every phase. So it's going to increase. So this 3 here is going to increase to 4 and then to 5 and so on. And obviously this is capped at V, right? Because we can't have more, we have only simple paths and those are maxed out at V. That's a general gist. So we can construct the layer network in using a BFS, right? BFS treated as that again in O of V. To find the blocking flow, we use something similar to DFS, and we can do this in VE time. And our final complexity, we just add this together and we do this V times, and we get O of V squared E. I put DFS in asterisks because it's not exactly DFS, because it has to keep track of like the maximum flow it can push through. And it's kind of like, you kind of think of it also as like pushing a whole class, a whole family of augmenting paths through the entire network at once instead of just one path at a time.
Wait, so how do you find a blocking flow?
You just, here, let me show an example. So for this, right? So you take the layer network and you try and find a blocking flow. So it's kind of like you DFS down here. So the maximum amount of flow you can push is 10, right? So you push 10 and then you look at one of its children. You push as much as you can through its children. So in this case, it's capped at 4 and you push it all the way to the sink. Since you're working on the layered graph, it's guaranteed to reach the, well, it's not guaranteed to reach the source. If it isn't guaranteed to reach the sink, but if it does reach the sink, then you back up and you update these. So you go traverse all the way down. If you reach the sink, with the maximum flow you can push through this graph, you keep track of it, and then you go back and you update. And you update this to 4, update this to 4, update this to 4. If it doesn't reach the sink, then you don't update anything because that path doesn't really matter. And then when you come back up, you try this path. You see, okay, I can push the rest of this 6. I can push it all into here. And then you push it in, you reach the source and you update it. So it's 4, or it's 6 out of 10, 6 out of 8, and then this is 10 out of 10 because you add in the amount you push through this path. And you go back and you try to push this way. And obviously you have infinite through there. Yeah?
So it's kind of like how you might try to solve max flow by greedy.
Yeah, but it only works, see, this blocking flow thing only works for these types of, this DAG right here, directed acyclic graph, which is cool because we can just repeat this again and again. So this way, right, we put 4, and we see it, or we push 10 through, but we don't know yet that we can only push 4. Then we push 9 through here, 9 of the 10 that we've already pushed into here. And then we can see, oh, we can only, this is 6 out of 10 right now, so we can only push 4 more here. And then we see, oh, we reached the sink. So we update 4, we add 4, and we add 4. So it's just like a DFS.
And then you're claiming that every time that you do a blocking flow and then put in the like put in the corresponding back edges if necessary, that the distance from the source to the sink will increase by 1.
Yeah.
Okay.
Yeah, that's the claim. I'm not going to go into the details, but yeah. So we repeat this process again with this new one so we can construct a new residual graph. This layered network now looks like this. Note that it's from this node is not possible to reach the source or to reach the sink. So your only path that you need to do here, the blocking flow here is 5 along this path. You add that in, and then this is there's no possible way to reach the sink, so you're done. And you can see here, this goes from 3 to 4 and to 5. There's no possible way to do this from 5, so you're done. But yeah, this is really complicated, so we don't really think too much about it. But yeah. So we're going to implement it by copying it from CP algorithms because we love CP algorithms. And a special thing about Dinic is that for unit networks, so edges that only have unit capacity, so that could be something we're about to talk about, the complexity gets really fast. It goes to e square root b, which is awesome. So we can solve a lot bigger problems with this. Yeah. So the special case that I was talking about is this thing called bipartite matching. So this is another interesting case where we can apply max flow to something that doesn't seem like max flow. So bipartite matching is a matching on a bipartite graph. So what is a bipartite graph? So that's a special type of graph where the nodes can be divided into two sets such that edges only go from one set to the other. So it's kind of like the opposite of the min cut thing where you can only have edges within a set. In this example, you can only have edges between the sets, which is cool. And a maximum bipartite matching is what we want to find, where we can link up choose as many edges such that no nodes has more than one edge connected to it. So yeah, so in this case, we want to match up as many applicants as the jobs that they apply to. Or maybe these relationships mean something else. Maybe they mean worthy of or something. But yeah. So we can represent this as a flow network. And we just go from the source. We connect one side to the source, one side to the sink. And then we have all these be unit capacity. Because if we can apply this flow, then it's success. You link them up. If not, then you just reverse, then there'll be no flow through them. And note that these also have to be unit capacity because each job can only accept one applicant. If a job can accept 2 applicants, 3 applicants, maybe you can increase this to 3, right? Or 4. That could be an interesting problem. And also for applicants, maybe instead of applicants is something else. And we can solve this really quickly using Dinic. And problem B, so this is problem that is very related to what I just talked about. So if you guys want to look through it, it's pretty interesting. It's not just doing bipartite matching, we have to do something else as well. So I'll give you guys a few minutes to read over that. All right. Hello. All right, cool. Can you hear me, Jacob? Okay. All right, so what is the idea with this problem? So obviously it's a bipartite graph, right? So we have the connections between the factories or toilet paper or whatever to the airports. But it also has weights, right? There's a certain cost to building a road. So how do we kind of figure it out? Any ideas?
So you could think about, okay, what can I answer the question? Is it possible for me to solve this given like D days? And then it's like, okay, then I'll just build all the roads that take D or less time, and then run like bipartite matching to see if that is enough. And then you realize that you can binary search to find the minimum.
Yeah, because the idea is that it's equivalent. So let's say you have a certain amount of days. So you say, okay, you have 20 days, right? It's equivalent to saying, because the problem introduces it as, okay, you can only build N roads. But you don't actually have to think about it that way, because if those N roads are all less than 20 days, and there are more roads that you could possibly build, you could just build all of them, and you don't have to think about selecting them, because N is equal to the number of airports. So obviously, if there's a maximum matching with all the roads that take less than 20 days, then you just pick N of them that work in the max matching, because you don't need to find them. And actually, when doing max flow, you can actually return like the edges that you actually use. So if the problem was a little bit more involved, it would ask you to return the roads themselves. But yeah, so this has kind of the property of a binary search, because you have, if you're below the certain amount of days that you're trying to look for, it's impossible. It's not possible. But if you increase it and it's a greater than, right, it's all going to be possible. So it's like you have an array that's like all false for smaller numbers, but it's all true for larger numbers. It's not going to be like an intermittent mix of true and false, or possible and impossible. So we're going to do a binary search. And since each simulation only takes e square root v time, and binary search will only take log d time, then this will fit in time. Actually, when I solved it, I binary searched over the days, but actually it TLE'd, which is really weird. So you can also binary search over the roads themselves if you sort them by the cost of the road. So how much time it takes to build the road, because that's equivalent, right? So
That's
you're just
big
searching
brain.
over a smaller space. What are you saying?
I said that's big brain.
Yeah. So you don't need to, it actually saves it by a fair bit because it's 10 to the 9 versus what? How many roads are there? 10 to the 5? Yeah, it saves it by what, around 10 operations or something. You only have to do bipartite because the costly part is the bipartite matching. So if you can even decrease the binary search by a few, by 10 or so, or by 8, it'll speed it up a bunch. Yeah, and that's pretty much it. I wonder how much time we have. We don't have too much time, so I was gonna implement it if we have time after, but I have a few things I still want to say. So that's the general idea. Yeah, one more thing is that when you're doing like bipartite, make sure you connect up stuff properly, because you have to create like a fake node, or you'll have to create a source node and a sync node that's separate from all the nodes they tell you. And so yeah, so I was gonna work through that if I do the walkthrough programming. So if you have any questions, comments, or concerns, please fill out the feedback form. I found this clip art that look cool. Yeah, this probably doesn't fit the contrast thing that we talked about in all hands, but it's okay. So practice resources, we have some problems for you. The bottom two ones are from CSCS, CSES. So those are just canonical problems for min cut and bipartite matching. But the other ones are pretty interesting. Notably, darkness, I think, is really interesting. If you want to take a look, it's interesting because it doesn't seem like a max flow problem, but it does. And actually, surprise, there's a bonus question because I figured this out yesterday, and it's pretty cool. It's really cool. If you guys want to take a few minutes to read open pit mining, this is a problem in one of the trainings that we hold for the regionals teams. And yeah, okay. Hope everyone has some time to read the problem. I'm gonna go over, there's no slide kind of going over the statement, so I'll just kind of explain it. So it's like you have a bunch of blocks, and each block gives a reward if you mine it, right? So it gives kind of like, I don't know, you can think of it as money. You can sell it for a certain amount of money, and you need to break it down though, and that takes a certain amount of cost. But for some of the rocks, are they rocks or blocks? They're blocks. For some of the blocks, you have to destroy other blocks that are obstructing it. You have to destroy all of them that are obstructing it to then cash in and take the block that has like dependencies. And this can be like chained together. So if one block is dependent on another block that's dependent on another block, you have to remove all the blocks that are dependent on it before. So you can kind of think of it as like kind of a graph. There's kind of like a graph happening there, which is kind of like a red herring because the solution kind of collapses everything together. And you don't actually care about the graph too much, at least. But yeah. Yeah, does anyone have any ideas? It'd be crazy if you guys did.
I mean, you could probably use Dijkstra to figure out like the cheapest way to. Actually, never mind. That's just trivial. It's trivial to figure out the cheapest, like how much it's gonna cost, like reach a certain block, because you just have to clear out all the dependencies.
Yeah, and there's only some. It was a 200, so you just try everything. Like for each one, you can do an n squared sweep, right? You can figure out all the dependencies like that. Maybe not a sweep, but like something similar to DSU could also work to figure out the list of like dependent ones, the blocks that are dependent on the other ones, the set of blocks that a block is dependent on.
You can just do a like a reverse DFS.
Yeah, reverse DFS. Yeah, that would probably be better. You figure out all the ones in the subtree. Yeah. So okay. Yeah.
So this whatever this dependency graph is, it's like async, right? Has to be.
Yeah, it has to be. Yeah, it has to be async. Or else.
Not do some greedy things like, look at the thing of all the options you have to dig in. Look at the one that finds the highest value of the EI minus CI or something, and then do that and keep repeating. Why would that be suboptimal?
I think it has to do with the fact that like, it's like, yeah, because it's not like one block, because it's like, I don't know, layers, like, because some blocks may be dependent on like a, on like, so they have, each block is dependent on a set of other blocks, and their intersection might be like interesting in the way that like, there's some set in that set of like dependent blocks that are shared. And it's kind of like, you have to think of, I don't know, like I think that's what makes it kind of interesting where you can't agree.
So you only care about like the value minus cost, right?
Yeah, value minus cost.
Oh, I guess, okay, one other observation is if this was a tree, then it would be easy because you can just solve it for like subtrees and then combine.
Yeah, so that's what I was thinking when I first saw the problem. It's like, okay, you just pick a subtree, right? The thing is, it kind of like merges together at some point. It's not a full tree, right? Where you mine the top one, then you can reveal more. It could be like connect out and then connects back and so on, right? Where the top one is like, oh, you mine block A, then you can mine block B and C. And then block D is dependent on B and C. So you don't pick like a subtree, you pick like a sub DAG, which is weirder.
Right, tree would be much easier.
Yeah, you could do, yeah, you could, I think, yeah, that sounds right.
Yeah, it's like I think it's called like an upper ideal in a poset or something.
Yeah, sure. Okay, if no one wants to keep thinking, I'm gonna reveal the official solution. 2 minutes. Okay, we'll give 2 minutes to keep for Nikhil to think, and then we'll reveal the official solutions, which are very confusing as well, because it's a single slide and it's a sketch, and it's like 5 bullet points. So, all right, we'll give like 2 minutes.
Is it relevant that the value and cost is suspiciously small? Or like, would this problem work equally well with the value and cost like integers?
I think
like
are large integers. Yeah, I don't think it's that important that the costs are small. Yeah, because that could kind of suggest like, I don't know, a DP, like,
yeah,
something. This problem is written in a way that's like suggests so many ways of approaching it.
Also, okay, I like, if you can solve this problem, then you can also solve the like derived problem, maximize the ratio of, say, like reward to cost, and by introducing another parameter and then like t, and then we solve this problem for profit defined as like t times cost minus, or I don't know, like reward minus t times cost, and then you binary search on t.
Wait, why would you multiply? Is this a more general problem? What?
Like
That's interesting.
So I've seen this style of problem, but like a different generalization. So it was for a tree, but the question was asking what's the maximum ratio, or like, I think the actual question was like what's the maximum. You have a bunch of cities which each have a population, they're connected in a tree network, and you want to pick an upper subtree that has the maximum like average population of a city. And so then what you can do is solve this problem. Like, so if you could solve this problem, then you can solve that problem for a DAG and not just a tree with that binary search trick. But I like that just black boxes the solution to this problem.
Yeah.
So,
yeah.
So I don't know if that helps. I don't think it
does. Oh, that would be a cool customer problem. Okay. Nikhil, you good? It's the great reveal that's not actually that great because it's still very dense. Okay. ta-da, here's the official solution, the official sketch. So, okay, first item. For each block, represented as a vertex with a value of W, which is dependent on its value minus its cost. So this is just compressing the problem. So basically, blocks are either positive value or negative value. So basically, if you mine it, you're losing cost, or you're losing your money, or you're gaining something from it. Okay, that makes sense. And for each relationship, if I blocks J, then we're going to add an edge from J to I with infinite capacity. And this will be apparent why we do this shortly. So J to I, not I to J, we go from J to I, we go backwards. It's interesting. And then for our source, we're going to connect the source to all blocks with positive value. And connect the sink to all blocks with negative value. And what we do is, to find our answer, we just do the max flow of that graph, and we take the sum of all the positive value blocks, and then we subtract the max flow. And that's our answer.
Wait, so we're trying to maximize something, but that means we actually maximize something else and then subtract
and
that?
We minimize it, yeah.
Yeah.
Which is really weird. This is so weird, okay?
Like the Morgans.
Kind of, because we're reversing it. We're reversing the edge. So yeah, it could kind of be like the Morgans, maybe.
Yes, it's like building the flow graph is like constructive, which doesn't work for the AND relationship of the dependencies.
Oh, I see.
So it's like infinite. So.
Yeah. Wait, Ryan, what's your point? You're kind of quiet for me.
If this solution feels kind of like De Morgan's law, or like putting a not on the outside of an and or expression, that flips the and or, because here, the blocking relationship is like an and expression where in order to unlock one block, you need to unlock all like the product of like the other blocks. But because building flow graphs is constructive, there's no way to represent that. So the only way,
it's like an or, like solving.
Solving the flow is like an or. That's interesting.
Okay. So what's the idea with this? So I'm gonna kind of go explain each part. So what does this graph, this max flow network represent? Okay, so we break it down to some value, right? So just make it a little easier. And then we want to choose a subset of the blocks so that its value sum is greatest while satisfying some constraint. And the constraint is like the dependencies that we have, right? So each flow network, the flow network represents each positive. So for each positive block, it needs to pay off its debt. So it has a set of dependencies. That's why we do it backwards. So if we pick a block and we want to attempt to get it, right? We have to pay off all of its debt. That's why the edges from J to I have infinite capacity. So we can spend as much money to pay off the debt. And then that is then subtracted right here with this part to the sink. So it's like we gain a bunch of money by breaking this block down, but we have to spend it to pay off the debt so that we can make a profit. So let's break this into cases to see why this works with max flow. So for each positive block, there's two cases. Either the debt is too large and we don't want to pick it because it would cost too much to get it. So if it's too large, then the max flow through the vertex I is exactly equal to its profit, right? So we push all the flow through. It's not enough to fill all of the dependencies, right? To fill the edges from the negative blocks to the sink. So those have a certain cost, right? So we need to fill that all the way, but we can't. So that means our flow increases by Wi, which is positive, and it cancels out with the summation that we have. So we don't try to do that. However, if it's fine, if we can pay it off, then what we do is we don't spend all of the profit that we get from the block to kind of fill all of the empty edges that lead into the source or lead into the sink from the negative blocks, from the debt blocks. And what's interesting is that, does that idea kind of make sense? Where you have like, okay, so it's like, you can think of it as 4 columns, right? So it's just like kind of like, not really like Bipartite, but you have 4 columns. So you have the source, then you have the positive blocks, you have the negative blocks, and then you have the sink. So the center line between the negative and positive blocks is like kind of like, so those are all your dependencies. So if a block is dependent, you can find out all the blocks that a positive block is dependent on, and you connect them all up to the negative blocks, right? So, and since the edge weight from the source to a positive block is equal to like the value of the positive block, that represents how much value we're getting out of that block if we push a flow through. And we push all that value that we gain through it, it distributes to all of its like debt blocks, and then those are capped on the edges from the negative blocks to the sink. And those are capped based off of their debt value, how much we need to pay them off by. So we distribute the profit that we make amongst all of the debt blocks that we have, and the max flow maximizes this and forces either you spend all the money that you spend all the profit into paying off the debt, or you have enough money that you have money left over after you've paid off all of your debt, after that flow has been maxed out. And the edge from the source to the positive block still has residual capacity. You don't have to spend it.
What is precisely the quantity that the max flow is capturing? What does this max flow correspond to?
It corresponds to.
This is not profit, right?
Is there an interpretation as
how much you have
cut?
to spend? It's how much you have to spend clearing the blocks behind all of, like the positive value blocks.
Can we, what happens if we think about the max flow as a min cut? Because if we're saying if it's a min cut, then we're back to actually maximizing.
The thing is, it's not cutting anything because the dependencies in between like the positive and negative blocks, they're infinite capacity. So it's not like we're cutting anything. We're not cutting anything on the left either, because it's possible to find the max flow and not have it fully, like not have the residual capacity be 0. Well, okay, we are finding a cut, but the cut isn't like straightforward where it's gonna cut all of the right side or all of the left side or all the middle edges. So I don't think you can think about it that.
So here, when you set the flow set, again, it's the total amount that's left after we pay off the debt.
No, it's total amount that we spend paying off the debt. And that's why we subtract it from the profit that we get, which is the positive summation of all of the block values. Yeah. I should have maybe made a graphic, but yeah. Good. All right. So, okay, and then one more thing is that it's interesting that positive blocks can share their debt if they have the same block dependencies. So if you have 2 blocks that are worth like 100, both worth 100, and then they're dependent on 3 blocks that are worth 50 each, right? They can share that payment of 150 amongst themselves, and the max flow won't exceed 150. It'll be equal to 150, and they'll both be able to pay off the debt. So it kind of introduces that also, like sharing things. So this is how it accounts for the fact that it's a DAG instead of a tree, because it accounts for like shared dependencies. Yeah. Yeah, this is a doozy. Doozy. Disney. Yeah.
Wait, okay, so, I still don't get it.
yeah, it's what is tricky? What is unclear?
Okay, so we're connecting the source to the positive blocks.
Yeah.
And we
And
connect.
the weight of each of those edges is equal to the value of the positive blocks.
Right. Okay. And then we hook up the the positive to negative blocks, or like all of the blocks with their dependencies.
Yeah. And you only hook up to the negative ones. You don't hook it up to the positive ones, which it's also interesting. I thought about that.
You mean you leave out like positive dependencies?
Yeah, and negative dependencies.
Okay. Interesting.
I think the heuristic is that it's never optimal to just, you kind of aiming to pick a subset of the positive blocks, basically. Not even a subset of all the blocks. You're picking a subset of the positive blocks and like trying to pay a minimum price for it by satisfying all its dependencies. So there's no need to try to connect up the negative blocks, because you never try and go for them anyways.
Okay.
Yeah.
And so then, okay, and then if we have a flow, then we interpret that as choosing.
Yeah. There's a lot of cases that you can think of that are really weird. Like, for instance, if you have like a really valuable block that's dependent on, I don't know, 3 negative blocks and a positive block. So the really positive block is dependent on a positive block and like 3 negative blocks. And then the positive block that the very positive block is dependent on is also dependent on the 3 negative blocks. And it's like, you need to do 4 things. You need to get 4 blocks to get that really positive block, and one of them is positive. And that case is actually accounted for because you're paying off the debt of the small positive block with the big positive block, and you can get both of them. Yeah. Yeah. So the small positive block doesn't need to worry about anything.
Okay, so I feel like can we try to say that this is a like weighted minimum vertex cover of a bipartite graph, where the bipartite graph is like dependencies from positive blocks to negative blocks, and then like if we take a subset of blocks which like where all the dependencies are satisfied, then like the
Well,
then there are no edges from a chosen positive block to an unchosen negative block. And so what? All right, I don't know. I lost that train.
I thought of another edge case that could be confusing, but actually works out. The edge case is, I guess I should draw it out. Well, okay, I'll just kind of explain it and see if you can get it, Jacob. So you have a really positive block that's dependent on, I don't know, 1 negative block and another positive block, smaller positive block. And then that smaller positive block is dependent on a really, really negative block. Then if you construct the tree or the graph, right, it might have a problem. But actually, you connect all dependencies. So you'll connect the dependencies of your dependencies. So the really positive block actually is connected to the really negative block. So it pays off the debt of the small positive block by paying for the big negative.
You connect all dependencies?
You connect all dependencies, not just one dependency. So you travel down the you do the subtree thing, and you figure out all the dependencies, and you all right. You don't, this is one layer. You compress everything into one layer. So that's how you can share. That's the sharing part, is that even if a positive block is dependent on another positive block, the dependency of the second positive block are still accounted for in this max flow. Yeah, so you do all of them, not just the ones immediately one level down. You compress it all, and you can do that because it's just 200, right? So it's n squared, and you can check all of them fairly.
Yeah. Okay. So if you build this graph, right, and then you think of like, what is given a cut that doesn't use any of the infinity edges. All right. So this is a selection of edges on the left and edges on the right.
Yeah.
Such that for any unchosen edge on the left, all of its neighbors on the right correspond to chosen edges. So
yeah,
if you say, okay, we're going to call, like, our construction will then be the set of unchosen edges on the left, like the vertices corresponding to unchosen edges on the left, together with the vertices corresponding to chosen edges on the right. And because we negated the weights on the right, now we flip that negative sign again, and it works out. So that the sum is like total sum of weights minus min cut.
Yeah.
Minus,
because the idea is that the edges that you cut on the left side are the ones that are not worth it, right? It's not worth it to go for those positive value blocks. But the ones that remain are the ones that are worth it. And that results in the right side, those edges still exist, which means all of its dependencies must be cut. All those edges on the right side must be cut, which means those are like what has been paid for. Yeah.
Yeah. Okay. I think I understand it now.
Yeah. So cool. This is so cool.
Yeah, this is pretty cool. But I last year I wanted to do research in combinatorial optimization, but I never got to it. I did a reading course.
Yeah. So this is
all really
this is
cool.
a really general problem as well. So I feel like you can make some pretty cool problems with this. But yeah, this is a very interesting max flow, and I think this will be it for today. So thank you to everyone who came. I hope you guys learned something new. There are lots of interesting problems. If you do have the time, I would highly recommend you check out The Darkness, which is a very good problem. Also max flow related, but kind of odd. So would recommend. Thank you to everyone. If you're watching on YouTube, thank you so much for watching through all of the workshops. We really appreciate it. And yeah, be sure to smash that like button and subscribe, you know? All right. Thank you to everyone. And we'll see you again next quarter, next year. Yeah. Bye.